Hello everybody and welcome back, and hello to our online students. Today what we're going to do is take a look at something called hybridization. Hybridization is a way that we help to rationalize what happens with bonding and quantum mechanics. A while back I shared with you that quantum mechanics helps us to explain some things, but it breaks down in other areas. So what we have here is it tells us that VSEPR theory does not address atomic orbitals. So quantum mechanics helps us to understand where electrons are going, but we run into this problem. And so there's a lot of gobbledygook up here, but let me explain it to you this way. If we have a molecule like this, CH4, now this looks familiar because you had this one on your worksheet. So if you were looking at your worksheet, you'd say, all right, there's a carbon, there's 4 hydrogens there. I drew my Lewis structure. Looks like this, like this, like this, and like that. And so my steric number is 4. There's 4 things attached to this central atom. And if there's 4 things attached to this central atom like this, and there's no lone pairs, we would say that the geometry is tetrahedral. Awesome. And if we wanted to get fancy, we might try to draw this in 3 dimensions. And we'd say, oh, here's my carbon, and there's that hydrogen on the same plane, and here's one kind of coming out at us, and maybe here's one going away like that, and looks like that, and like that. And our art teacher is happy, and we're feeling pretty good, because our bond angle is not 90 degrees, is it? It looks like 90 degrees, but it's not. What is it? 109.5, excellent, 109.5. So I'm going to go 109.5 degrees and 90 degrees, and I'm going to, no. Okay, now, that's all review. And I'm going to show you something else that's review, and that is taking a look at the orbital notation of carbon. So carbon has an electron configuration of 1s2, 2s2, 2p, 1, 2. There's my electron configuration. And then if I do my orbital notation, I would have my 1s box here, 1s, and then I have my 2s, 2s, and then I'm going to have my 2p. And I'm going to go like this, there we are. And I'm going to throw in my electrons. Electrons, okay. How many electrons go in this first box? 2. How about this box? 2. And then as I come over here to my p orbital, this is my 2p orbital, I'm going to go like this. Okay. Now this is review as well. This is orbital notation. Any questions so far? Okay. Now here's where we run into a problem. VSEPR theory tells us that we should have 3 things attached to this carbon atom, and we should have bond angles of 109 degrees. VSEPR theory. Now when we take a look at quantum mechanics and we try to rationalize this and say, well, here I've got these 2 electrons, they're by themselves. And we know electrons seem to be happy when they're paired up. So how do we go from these 2 electrons to 4 bonds like this? 4 covalent bonds. It doesn't make sense. It doesn't add up. And so we have to do something called hybridization. Have you heard of a hybrid car? You people have heard of hybrid cars. What is a hybrid car? What does that mean? When it uses electricity and gas. Yeah, so we're taking 2 different things and we're putting them together, is the idea. So we're going to take quantum mechanics and we're going to take VSEPR theory and we're going to put them together and we're going to make a hybrid. And so trying to see where do these bonds match up? How do they match up? It kind of does, we're not sure. So I'm going to take this and I'm going to make a hybrid orbital. I'm going to take my valence electrons here, and I've got 2 and 2. I've got 4 valence electrons. Oh, 4 valence electrons. Wait a minute. Aren't there 4 bonds here? Yes, there are. Yes, there are. Okay, so I'm going to take my 4 valence electrons, and I'm going to take this s and this p orbital, and I'm going to put them together. So I'm going to take that s orbital. Here's my s orbital. And I'm going to attach that p orbital to it like this, okay? And I'm going to call this my sp3 orbital. This is hybridization, sp3 hybrid orbital. It's an s and it has 3 p orbitals. And I'm going to take my 4 electrons now, and I'm going to add them like this. So this is my sp3 hybrid orbital for carbon. And now what I can do is I can take and I can add my hydrogen atoms. And hydrogen atoms have how many valence electrons? Stick fingers up. How many valence electrons? 1. Thank you for using that finger. It each has 1 valence electron. So let me go back here to my Lewis symbols. I've got carbon. Here's my carbon. Here's my, okay, Lewis symbol. And then hydrogen. So right now, each of these valence electrons match up with my hybrid orbital here. And then each of these hydrogens bring an electron like this. And now we end up with 4 covalent bonds attached to that carbon. So this is us trying to rationalize how this works. Any questions? Okay. Well, you folks are handling this really well. Okay. So now what we're going to do here is we're going to find out that there are lots of different types of hybrid orbitals. And I could go through all of this. You could go through all of this, but there is an easier way to do this. There was a student a while back who just said, hey, Professor Locken, this is the way we learned it in high school, and it works really slick. And then she showed it to me, and I was like, that works way better than what I had planned. Let's go with that. I like that idea. So we're going to do that. Now, these bonds that we create here, these bonds, we call these bonds here, where you're sharing 2 electrons, we call these sigma bonds. It's like an O with a line coming across the top like that. We call that a sigma bond. That's one type of bond. We're going to see that there's another type of bond coming up here in just a little bit. So that's a sigma bond. It's a sigma bond. Okay, so here's the shortcut that the high school teacher showed the student, and then she showed me, is there's all of these different hybrid orbitals, and how do you know which ones to use? So here's what she did, is she said, well, we're going to use our steric number, and then we're going to do our hybrid orbitals. Our steric number and our hybrid orbitals. And I'm going to show you what these are, and then we're going to see if you can't find the pattern, because I'm not a big fan of memorizing things. So if our steric number is 2, and there's a slide for this here. If our steric number is 2, our hybridization is sp. If our steric number is 3, it's sp squared. 4 becomes sp cubed. 5 becomes sp cubed d, and then 6 becomes sp cubed d squared. These are the different orbitals that we're hybridizing. Now that's a lot to try to memorize. Can anybody see a pattern in this that might make this easier? If you add up the S's and the P's, yeah. If you add up S, P's, and D's, you get the steric number. Yeah, so for example, SP3, that's 3 P's, that's 4 letters. That gives us a steric number of 4. Yeah, that's what this student shared with me, is like, oh, that is so much easier than doing this. I like that. So it's kind of a shortcut. Now, it's good to understand where it all comes from, but this, for me, is easier to remember. So nicely done. I like that. Okay, so then let's try actually applying this. Determine the type of hybrid orbitals necessary to rationalize the bonding of boron trifluoride. We've got boron trifluoride. Boron trifluoride. Hey, thank you for helping me out. You did an awesome job. Could you help me find somebody really smart to help me out here? Derek. Hey, Derek. Hey, how are we doing? Awesome. Hey, Derek, help me out here. I need to do the Lewis structure for this. And there's 5 rules for this. And the first rule tells me I need to add up the number of valence electrons. Derek, you're a pro at this. Okay, so boron has how many? 3. 3 valence electrons. Fluorine has how many? 7. But there's how many? There's times 3. All right, so if I add that up, Derek, just to make sure I'm doing this right, that's 21 plus 3 is 24 valence electrons. Is that correct, Derek? All right, awesome. Thank you, Derek. For those participating today, we have these fabulous consolation prizes. Calcium carbonate. Yes, calcium carbonate. Tastes like chalk, looks like chalk, writes like chalk. Derek, could you help me find somebody really smart to help me out here? That's okay. We're all friends here. Who, help? You can describe. What color shirt? Here. Hey, hi. What does your mom call you? Victoria. Hey, Victoria, thank you for being here today. Derek, thank you for introducing me to Victoria very much. I appreciate that. So Victoria, I need to draw the Lewis structure for this. So Victoria, what's going to be my central atom? Boron. Thank you. And then what are going to be my peripheral atoms? Fluorines. So I'm going to make single bonds here to my fluorines. Single bonds to my fluorines. All right. Then Victoria, I think that was step 2. Now step 3 is I need to complete the octet of these peripheral atoms. How do I do that? What do I do? Add 6 electrons to each fluorine, right? So 1, 2, 3, 4, 5, 6. I'm being a smart ass. How do I do this right, Victoria? Okay, thank you. There's one in every crowd, right? Okay, like that. Okay, Victoria, now that I've completed my octets here, 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 I need to do a little comparison. What am I going to be comparing? Yep, add all the electrons up, see if they match. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've got 24 electrons. We're good, right? Okay, so we've satisfied that. Then the last rule says if you need to, you can make double bonds. Should I make a double bond here? And people are shaking their heads. No. But normally you might think you would, but we don't make a double bond here. Why don't we make a double bond for this one? Boron does not satisfy the octet rule. Yeah, it's one of those exceptions. Nicely done. Okay, so Victoria, I need another smart person just like you. Can you help me out? Emma. Emma. Hey, Emma. Thank you for being here today. Emma, I need to figure out what the steric number for this is. Is it 3? Is it 3? Yes, Emma, rock on. Okay, so Emma, if the steric number is 3, what's the hybridization? sp squared. How did you know that? Because I just said it? I was covering this up, but you knew it. Nicely done. Nicely done. I'm just picturing a test type question where I give you the formula and I ask you then, what is the hybridization? Can you do that? Yeah, you'd have to draw the Lewis structure, and then from the Lewis structure, you can figure out the hybridization. So nicely done, Emma. Nicely done. Then let's try something a little trickier here. Sometimes we have molecules that are a little bit more complex. They have more atoms attached. In fact, they have more than one central atom. So for example here is methanol. Methanol is the type of alcohol that if you drink it, you go blind. This is the bad stuff. Now, as we look at it, you've got a carbon and you have an oxygen, both of which could be considered as central atoms. Both of these could be central atoms. And so the carbon atom, we might think of that as having 4, a steric number of 4. And let's see, its geometry would be tetrahedral. And its molecular geometry would be tetrahedral. But our oxygen, oh, wait a minute, why is that? Why do I have that? Oh, yeah, I remember why I have that. Who's this up here? Does anybody know who that is? Oh, wonderful, Gromit. Yeah, that's some of my favorite movies. I love Wallace and Gromit. Did you know that the moon is made out of cheese? Yeah, totally is. Yeah, and if you're not sure, you're going to have to YouTube Wallace and Gromit. Now, when I look at this molecule, the ball and stick molecule, it looks like this. And it just reminds me of Gromit. Because you got the 2 legs and the head up there and then the back legs. Well, maybe it's just me. But now if we want to figure out the oxygen atom there, let's take a look at the hybridization there. Hey, Emma, you did a fantastic job. Could you do me a solid here? Could you help me find somebody just as bright as you? Tiana. Say, Tiana, thank you. Thank you. Hey, did you know Victoria is in class too? Yeah, do you two like know each other? Yeah, oh, that's cool. Okay. All right. So Tiana, we just did all this information about the carbon atom. Let's talk about the oxygen atom there. What is the steric number on that oxygen atom? It's 4 because we count the lone pairs. Yeah, nicely done. So if the steric number is 4, what's the hybridization? sp3. Nicely done. sp3, 1, 2, 3, 4. 4 things, right? 4 things. Yes, yes. Wait, did you say sp3 or sp2? sp3. Okay, yes, sp3. All right, thank you. Now, if it's sp3 hybridization and our steric number is 4, here's the tricky question. What is the molecular geometry? The molecular geometry. It's bent. Nicely done. It's bent. So our steric number is 4. We have 2 lone pairs. It is bent. So, Tiana, when people look at this molecule and they are asked the bond angle, they'll look at that and they'll see 180 degrees. But we know it's not 180 degrees. That would be a lie. Because we're too smart for this. Emma said that you were smart, and I believe her. So the bond angle on this is not 180 degrees. What would you predict it to be? 104.5. Brilliant. Yes, 104.5. Nicely done. Nicely done. All right, so for a little bit of practice here then, here's what I want you to do. Here we have a molecule. This is called 1,1-dimethylhydrazine. 1,1-dimethylhydrazine. I would like you to try drawing the Lewis structure for this molecule. And then it's going to ask us then, what is the hybridization of the two nitrogen atoms in this molecule? And then what would you expect the nitrogen-nitrogen-hydrogen bond angles to be? Now, drawing the Lewis structure for this, there's some clues to it. I'm just going to write this out here. We've got CH3, and then we've got two of those, and then we've got nitrogen, nitrogen, and H2, like that. I think I have that there. Okay. Now, this is organic chemistry. We've not talked a whole lot about organic chemistry, but in organic chemistry, if we read the formula going left to right, it gives us some clues. So, for example, there's a carbon with 3 hydrogens, and there's 2 of those. And they are attached to a nitrogen, which is attached to another nitrogen, which is attached to 2 hydrogens. So there's some clues in this. So go ahead and take a few moments. You can check with your neighbors, see if you can draw the Lewis structure for this molecule, and then we'll try to answer these questions. Picking people completely at random. You, back there, yes, you had this correct, I believe. Yes, yes. So can you help me out here with our structure? We want to come up with the structure for the 1,1-dimethylhydrazine. So how did you do this? A lone pair up here. Excellent. Okay. And so then we fill the hydrogens like this. I'm running out of board here. Okay. That's okay. No, this is my fault. I started at the top. And then more hydrogens like this. Okay. Nicely done. So this is correct. And if you have, say, this CH3 down here and the lone pair up there, that's fine. And if you have the lone pair maybe where the hydrogen is and the hydrogen up there, that's still fine. It's the same thing. It's the same molecule. So nicely done. Any questions on this? Okay. Now it does ask us here, it says, what is the hybridization for the 2 nitrogen atoms in this molecule? So the hybridization means we're going to have to figure out the steric number on our nitrogen here. So our steric number is 4. Okay, so our steric number is 4. And if our steric number is 4, then our hybridization is going to be, I erased it. Oh dear, how will I ever remember? If the steric number is 4, which one of these would it be? sp3, because it's an S and 3 Ps. Okay, so sp3. And this nitrogen is the same. It's the same thing. So any questions on that? Okay, then the last question I think here it asks is, what would you expect the nitrogen-nitrogen-hydrogen bond angle? So nitrogen-nitrogen-hydrogen or nitrogen-nitrogen-hydrogen bond angle. It doesn't matter. It's the same thing. What is the bond angle? Oh, this is tricky. Now, we worked with you. Can you help me? Yeah. Can you help me find somebody else? Hey. What does your mom call you? Sawyer. Okay, so Sawyer, I want to figure out what this bond angle is here, which is the same as the bond angle here. Now don't say 90, because that's just the way I drew it. Okay, so Sawyer, how might we go about this? Look at the table you made. Yep, yep, yep. Yeah, less than 109.5 degrees. How did you know that? What did you look for? Yeah, so steric number of 4, one lone pair, bond angle is less than 109.5. That is brilliant, Sawyer. Absolutely brilliant. Now, as far as test type questions go, here's one for you. Which designation describes the hybrid orbitals on the carbon atoms in this molecule here? Okay, what would be the hybridization on the carbon atoms? So take a moment and check with your neighbors, see if you concur. Now that you've had a chance to check with your neighbors, let's see what our consensus is. You two were chatting with each other here. Did you agree? Okay, so what did we agree on? What is the hybridization? It's sp2 because our steric number is 3. That double bond counts as one thing. So that is sp2. Nicely done. Then how about this one here? What is the hybridization of each carbon atom in acetic acid? This is vinegar. So we've got 2 carbon atoms going left to right. What is the hybridization? Check with your neighbors. Did you two talk? Yeah. And did we come to a consensus? Fantastic. Oh, shh. Okay. So help me out here. What are your thoughts for the hybridization of these 2 carbon atoms? You said C was the answer. So C is sp3, which means we must have a steric number of 4 on the first carbon atom. That seems right. And then the second carbon atom, you said sp2, which means you must have a steric number of 3. And there are 3 things coming off of that carbon atom. So nicely done. So if you come across a test question like that, you're going to totally rock that one. Nicely done. Yeah. Okay, I'm going to show you a shortcut here, actually. I told you that chemists are lazy, right? So sometimes people write them like this. Sometimes what they do is they say, you know, this here is 2 electrons, right? It's 2 electrons. So instead of drawing the dots, they'll go like this. That's 2, 2, 2. Those are lone pairs, okay? That's chemists being really lazy. Don't do that, because Professor Grunt, who teaches organic chemistry, if he sees that, he will throw calcium carbonate at you at high rates of velocity.